All right, as you can see there, today we're going to talk about fraction models. And to start out with, we're just going to talk a little bit about fractions. Fractions and rational numbers. They're very much related to each other. We've talked about the sets of natural numbers, whole numbers, and integers. Today we're going to go one step further and bring rational numbers into our discussion. First, I want to make the distinction between fractions and rational numbers. And a fraction is any number on the top with any number on the bottom. More specific than that, rational numbers have an integer on top and an integer on the bottom. And this will be our focus. An example of something that's a fraction but is not a rational number would be something like square root of 2 over 2. Square root of 2 is not a rational number. It's not a repeating or terminating decimal. It's an irrational number. And so while this would count as a fraction, it doesn't count as a rational number. Rational numbers are integer on top, integer on the bottom, and that's going to be where our primary focus is located. Just a little reminder that fractions have a numerator and a denominator. So if we have a fraction like 3/5, it's the numerator that's on top, the denominator is on the bottom. So that would be a fraction and sort of the components of that fraction. The numerator on top, denominator on the bottom. If you ever have questions about any of this, let me know. Otherwise, we're going to go forward and kind of look at some models that we're going to use when we work with fractions. All right, some diagrams. If we want to write a fraction by using some kind of diagram, there are 3 different kinds of diagrams we're going to look at. The first is the length model. The second is the area model. And the third is the discrete model that is also known as the set model. I think our book calls it the set model. I like discrete better because you have discrete items that you're looking at. They're distinct from each other. They are discrete, different from each other. They're separate. At any rate, let's look at what 2/3 would look like using the length model, the area model, and the discrete model. There's more than one way to write these. But the examples that I'm going to give just sort of show what these models are and what they look like. So if we want to use the length model, essentially what we're talking about there is a number line or a ruler. You can think of it either way. And we're just looking at distance. And if I want to put 2/3 on here, I could have 0 on one end and 1 on the other. And I can chop that up so that I have a marker for 1/3 and a marker for 2/3. And I can put 2/3 right there on my model. Not very complicated, but that's the length model. We're just talking about distance, and we just want to make sure we can identify the spot where 2/3 would be. Area model. This one's going to be really, really useful for us. This is probably the one where most of our focus will go over the time where we talk about fraction models. The area model. Basically, I'm going to make some shape. Typically either a circle or a rectangle. And I'm going to chop it up and shade it to represent the fraction that I've been given. Here that's 2/3. So for the area model, if I want to use a circle and I want to chop it into 3 equal pieces, it doesn't have to be perfect, but I've chopped it into 3 equal pieces. And then I'm going to shade two of these 3 pieces to show 2/3. It doesn't matter which 2 I pick, but I'll just choose those. And we've shaded 2/3 of that diagram. So using the area model to show 2/3, we've done that here. If you have any questions about these models or why we've drawn something the way we've drawn it, please don't hesitate to ask. Discrete model. This one's a little bit unusual for folks because it's just not something you see that often. But the discrete model, what we're going to do is we are going to make a picture of what 1 looks like, and then we're going to identify our fraction inside there. I guess that's kind of the same thing we did in the others, really. We identified what 1 looked like, and then we found 2/3 inside it. We identified what 1 looked like, and then we showed 2/3 inside it. And now we're going to do that with our discrete model. Because I know I'm after 2/3, I'm just going to keep this as simple as possible. We're going to make, there's 3 things. That would be 3/3 or 1 whole thing. And if I want to identify 2/3, then I just need to circle 2 out of those 3 things. I've identified 2/3 of that unit, that one full thing. So in the length model, we're looking at something akin to a number line or a ruler. Area model, we're going to use either a circle or a rectangle. You could use other shapes, but typically circle or rectangle to identify the fraction we want to show. And the discrete model, we actually have physical individual objects that we use to show the fraction that we're working with. Are there any questions on that before I give you a chance to try to draw a different fraction using each of these models? Awesome. All right. What I want you to do is just take a minute. There's not really a way for me to set up a poll for this, but I want you to try to draw 3/4 using the length model, the area model, and the discrete model. And then in, I don't know, in a few minutes, we'll come back together and we'll talk about it all together. I'm thinking maybe we'll go another 30 seconds. If you want more time, need more time, just let me know. That's not a problem. All right. Let's start out looking at the length model here. And again, your picture may not look exactly like what mine does, but if you've got the idea down, that's what we're really focused in on. The length model, I'm going to go from 0 to 1, and I want to identify 3/4. Well, to identify 3/4, it'll be good to cut this into fourths. I'll probably cut it in half first. And then 1/4, then 1/4 is over here. 3/4 would be over here. And then that's where my 3/4 goes. Again, if you have any questions about any of this, don't hesitate to ask. Last time we did area model, we did a circle. So I'm going to do a rectangle this time. And I'm going to have a rectangle. Because I'm looking to make 3/4, I want to cut this in 4 pieces. So I want to cut this in 4 equal pieces. Equal, it could be close. It doesn't have to be perfect. And then because I want to shade 3/4, I want to shade 3 of those 4 pieces. And I've showed 3/4 using the area model. Finally, the discrete model. If we want to do a discrete model and we want to show 3/4, I want to make sure I have 4 things total. And then when I go to identify 3/4, I single out 3 of those to be 3/4 of the entire picture. If that all makes sense and you're comfortable with that, that's great. We'll keep going. If you have any questions, let me know. All right, let's spend a little time with the length model. So our job is to place 5/6 on that number line. So I have a number line there, we want to place 5/6 on it. And you could just sort of try to eyeball it or get out a ruler and measure, but really what we want to do, if we want to put 5/6 on that number line, it goes from 0 to 2. What's the first number I should put on there? What should I do first to sort of orient myself a little bit better? What number should I put on there first? And it's okay if you're not sure, but if you have something in mind, yeah, I agree. Leslie, Jessica, yes. And Moylan, I hope you're going to type a 1 also. You can go ahead and do that because then I'll know you know. But yeah, we'll put a 1 on there. And now I'm trying to identify 5/6. So let's see. I kind of like to chop this into sixths then. Sixths might be hard, so maybe I'll do thirds first. I'll put 1/3 and 2/3. And if you think about these in terms of fractions that have the same value, I want to work with sixths here. Well, if I have 1/3, but I want the denominator to be 6, what would the numerator have to be over here for something that's equal to 1/3 that has a denominator of 6? What would this numerator have to be? 2. Perfect. When we create equivalent fractions, if we multiply the denominator by 2, we also multiply the numerator by 2, and so that would be 2/6. You don't have to do this necessarily, but just to sort of say, okay, well, that's where 2/6 would be. And then using similar logic, let's see, this would be where 4/6 would be. And so now I have 1/6, 2/6, 3/6, 4/6. So 5/6 is going to be right there. And that's how I can go ahead and identify it. Hopefully that process was comfortable and made sense. If there's anything about it that you weren't sure of, don't hesitate to ask. We identified 5/6 by first giving us that 1 to put us in the right place, and then we zeroed in on where 5/6 would be. All right. Determine the value of x on this number line. I'm going to make a poll for this one, and I want you to figure out where x is. Like using the length model, where is x? What is x showing? So what would the value of x be on this number line? I don't think it's necessarily an easy question, but I do think you can answer it. Use your problem-solving skills. Use your knowledge of, granted, it's relatively new, but of how the length model works to figure out where or what value that x would represent. There's a little bit of working with fractions that goes on in here. Naturally, we are working with fractions and fraction models. So we'll get a little bit of fraction practice sort of as an ancillary benefit of all this. Let's go another 15 seconds. If you want more time, let me know. But that's when we'll talk through this one. Let's see what we've got. Okay, pretty strong agreement, but not everybody is on that 5/8. Okay, so let's go back and take a look. Those of you that I can tell you 5/8 is the right answer here. Those of you who got 5/8 as your answer, what was the first thing you did? What was the first number you wrote down on here to help you find out where that X was? What did you do first? And really, it's just a fraction you can type, probably. The first step you took towards figuring out what X would be. And maybe not everybody did what I would anticipate, but what was the first thing you did to try to figure out what that X was? And like I said, 5/8 is the right thing. So if you got 5/8, you probably did this step first. And keeping in mind, the only thing we know is that that is 1/4. There's a couple of different ways you can think through this. You can think, well, it took me 2 jumps to get. Okay, yeah, that's it. Leslie, that's exactly where I was going. It took 2 lines to get to 1/4. And so if it takes 2 lines to get to 1/4, then half of that, halfway to 1/4 here would be 1/8. Because half of 1/4 would be 1/8. And that's an important piece of this. That, halfway to 1/4 would be 1/8. Because then if that's 1/8, then this would be 2/8. And then I guess another approach you could have done here is you could have said, well, what if I don't want to write that in fourths? What if I want to write that in eighths? Well, that would be 2/8. And if it's 2 jumps to get 2/8, then 1 jump to get to here must be 1/8. And once you know that each step is 1/8, now the rest of it falls out because that's 2/8, 3/8, 4/8, 5/8. And so X is at 5/8. The key here, I think, is taking the one thing that you know, that this is 1/4, halfway there is going to be 1/8. And now that I know what 1 unit is, I can count anything. And that's how we get to the 5/8. Sometimes a little hard to put into words what it is you did. I totally get that. Here's another question. Locate 5/6 on the number line. I'm not going to do a poll for this, but I want to give you a chance to try it. And then once you've had a minute or so to try to figure out where 5/6 is, then we'll do it together. What you'll find with questions like this one is kind of like we saw way back at the beginning in chapter 1, is there's not necessarily one right way to do it. You might come up with an approach that works for you that's different that somebody else uses. I'm going to show you what I think is most common and is most typical, but there are other ways to answer questions like this and still be correct. As long as your method is, valid and repeatable, it's okay. Essentially, we start out with the thing we know and go from there. I'm going to start working on this. If you're still working on it, that's fine. Just keep going and kind of take a look at ours and see what we're doing. If you have any questions about my process as we walk through this, you let me know. The only thing I know is that 2/3 is here. And that's 1, 2, 3, 4, 5, 6, 7, 8 steps from the beginning. So 8 steps from the beginning was 2/3. So if I do half of that, then that's going to be 1/3. So it's 1, 2, 3, 4 steps is where 1/3 would be. Now, that's all well and good. I'm trying to get to 5/6. So what I need to know is how big a sixth is. At some point, I need to know how big 1/6 is. Well, if I take that 1/3 and I cut it in half, that's going to be just 2 spaces, and that's 1/6. And that's sort of the linchpin for me here, because if I'm going to find 5/6, it's going to be really valuable to know how many steps is 1/6. And now I can see that 2 steps is 1/6. All right, so there's 1/6. This would be 2/6. That works with the 1/3. And I go 2 from there, and I would be at 3/6, which I could call 1/2 if I wanted to. And then I'll go 2 more, and that would be 4/6, which is the same as 2/3. And then I'll go 2 more, and that's where 5/6 would be. And that's the thing I was looking for. If you have a different approach that you want to share with us, that's great. If you pretty much did exactly that, that's really good too. If you aren't really sure what the heck's going on and you don't know how we got 5/6, it's okay to ask, because this is a new and different thing. This whole idea of modeling fractions may be totally new for you. And, I was fine when we were going from 0 to 1, and that's where 1/2 is, but this is a lot more involved. You're right, it is. But basically our key here is to figure out how to get to 5/6. We want to know how big 1/6 is. And once we know how big 1/6 is, we're kind of home free. Then it becomes a matter of just counting to the right place. Okay, let's see. What about the numerator? So we had 2/3 and we cut that in half and got 1/3. If that part's okay, we can go from there. Gotcha. Perfect. That's a great question. Okay, so going from 2/3 to 1/3 to 1/6 was okay, and then we're just going to count. So essentially, every time I go 2 spaces, that's 1/6. So 2 more spaces puts me at 2/6, and 2 more spaces puts me at 3/6. And 2 more spaces puts me at 4/6, and 2 more spaces puts me at 5/6. Got it? All right, that's awesome. Very good. Very good. That's terrific. So essentially what we did was, once we found out that 2 spaces was 1/6, we just counted 2 spaces as 1/6 every time along the way. Very good. I'm glad we fixed that up. If anybody else has questions, you can ask them. Even if your question, is a little bit hard to phrase, we'll dig it out. We'll get there. We got the 1/6 from the fact that we were here at 1/3, and so half of 1/3, which, since 1/3 was 4 spaces, half of 1/3, and if you want, you could do half of 1/3, and of is a word that tells us to multiply, so that would be 1/2 times 1/3. And multiplying fractions, we multiply numerators, multiply denominators, that's 1/6. Or, if we have half of a number, then we double the denominator. I'll say that one more time. So let's say we have the number 1/10. If we have half of that, it would be 1/20th, because it has to be half as big. So this has to get doubled down here on the bottom. And that's one way we go from 1/3 to 1/6, or you can think about it as multiplying those fractions. But that's how we get from 1/3 to 1/6, is because if we take half of 1/3, that's 1/6. Heck, we can use the area model for that. If I have my circle cut into thirds, and I cut one of those in half, now it's just 1/6 of the whole thing. I hope that cleared that up. If not, you can let me know and we can talk about it some more. All right. Okay, let's move off the length model for a minute and talk about the area model some. The area model is going to be really, really valuable for us with problem solving. And this is sort of the first example of that. Jose paid $12 for a box of chocolates that weighed 3/4 of a pound. What is the price for a box that weighs 1 pound? So he bought 3/4 of a pound for $12. What is the price that weighs 1 pound? And you might think of diving right into algebra for this or something like that, but instead we're going to use a picture. And what I'm going to do is I'm going to say, okay, what if I draw myself a 1 and he bought 3/4. So we're going to chop this up into 3/4. There's fourths, and he bought 3/4 of a pound. So what he bought was that much, 3/4 of that 1 pound box of chocolates. And he paid $12 for it. So my question to you is this: if he paid $12 for those 3/4, how much did he pay for each of those little rectangles? How much did he pay for each of those? If he paid 12 for 3/4 of a pound, how much did he pay for each fourth is really what I'm asking. $4. Perfect, Nicole. Perfect, Jessica. So what he paid was, he paid $4 for this one, $4 for this one, $4 for this one. Well, logic would indicate this one's also going to cost $4. And so if he were to buy the entire pound, it would cost $16. We didn't have to use algebra. We didn't have to use any sort of symbolic manipulation. We just used a picture. And the area model is great for that. We'll look at more problems with the area model later on, but that's sort of the basic idea of using the area model to answer a question. We can solve problems that we don't need algebra or hardly any symbolic manipulation at all. More of an abstract area model type question. If that rectangle equals 1, show 4/5. What would 4/5 look like? If that rectangle is 1, what would 4/5 look like? I'm going to give you a minute to do it, and then we'll do it together, and you can let me know if you have questions. All right, if I want to show 4/5, what I need to do is cut this into 5 equal parts. That's not always that easy to do. It doesn't have to be perfect. I'm going to cut it into 5 equal parts, so I'm going to need to draw 4 lines. Let's say 1, 2, 3, 4 lines. And so I have 5 parts. We're going to say those are 5 equal parts. That's how I meant to draw it. And so that's 5 equal parts. And if I want to show 4/5 of this, then 4 of those 5 pieces need to be shaded. And so we've shaded 4/5 of that rectangle. And that's kind of how the area model works with us when we shade it. If you have questions about that, let me know. Otherwise, we're going to move on and talk about the discrete model a little bit. If that is equal to 1, the first thing we're going to do is show 2/3. So we want to show 2/3 of that. I want to give you a minute to think about it. Actually, give you a minute to draw it too. It's 6 by 3. That 6 by 3 array or 3 by 6 array is our 1. That's our unit, that's our 1, and we want to show 2/3. Here again, there's more than one way you can do this, but sort of get you in the spirit of how we're going to approach discrete model questions is we're trying to show 2/3. So what we want to do here is we want to think about this in a way that gives us thirds pretty easily. And if I look at it, I've got this row, and this row. I have 3 rows. So if I look at those 3 rows, each one of those is 1/3 of the whole image. Let me know if anything doesn't make sense. Each one of those is 1/3. This row's 1/3, this row's 1/3, this row's 1/3. All together, they make one whole thing. And so if I want to shade 2/3 of this or identify 2/3 of this, then I'll just do that. And that's 2/3 of it. Let me know if that doesn't make sense. Let me know if you don't see how that's 2/3 of the whole thing. We want to identify where the thirds are and then circle 2 of them to have 2/3. Okay, get that out of the way. And now I want to let you try the second one, which is to identify 5/6. Take a minute. See if you can identify 5/6, and then we'll talk about it together. Since we want to identify 5/6, what we want to do first is kind of identify what is 1/6. Very similar to what we did with the length model. If I wanted to know where 5/6 was, it helps me a lot to know where 1/6 would be. It's kind of what we did with Jose and the chocolates. If I want to know what that whole pound of chocolate would cost, what helps me a lot is know what 1/4 costs. Once I know that 1/4 was $4, then I can answer the question. So we want to figure out where 1/6 would be. As I look at this, well, those are thirds, and I guess I could cut those in half, but that's a little clumsy. How about instead I look at it in terms of these columns, because there are 6 of them. Since there are 6 columns, each one of those is 1/6 of the whole piece. Each one of those is 1/6 of the whole. So if I want to identify 5/6, then what I'll do is I'll just circle 5 of those 6 columns like that. And that's 5/6 of the whole picture. Hopefully that makes sense. Hopefully that went well. If not, if you have questions, just let me know. Awesome. Hopefully those 2 are comfortable. This third one, I think this third one's pretty difficult. This third one is not going to be a focus for us. 4/9. This is not going to be a focus for us, but I do want you to see it. To do 9ths, really, to cut this into 9ths is going to be pretty hard to do because, I saw that I could cut it into thirds by looking at the rows, and I saw that I could cut it into 6 by looking at the columns. To cut it into 9ths, though, that's pretty clumsy. What I'm going to have to do to cut it into 9ths is I'm going to have to make little groups of 2 so that I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So each one of those little groups is 1/9. Now, if I want to identify 4/9, what I'll need to do is find any 4 of those and circle them. And so that would be 4/9. Again, these 2 are going to be our primary types of problems. This will not be a focus for us, but I wanted you to at least see that it can be done. Okay, let's look at another discrete model question. If that equals 1, show 1/3. How would you show 1/3? Take a minute, sketch that out, decide where 1/3 would be, and then we'll do it together. We've got a 3x4 array. We want to show 1/3. I'm hoping what you did was, and there's 3 different ways you can answer this and be correct. Either that way, that would be 1/3, or this way would be 1/3, and probably less common, but also correct, would be that way, would be 1/3. Essentially, we're identifying 1/3 of this diagram by picking one of the rows to circle. Let me know if you have questions on that. There would be 1/3. All right. A little bit different, going the other direction here. Now we're going to say that this whole picture is 4/3. Up until now, the picture's been 1. But what if that picture is 4/3? How would we identify 1? I'll give you a little bit on this one to identify where 1 would be. If that whole picture is 4/3, what would 1 look like? All right, let's take a look then. So if that's 4/3, now, up until now, I've always been concerned with the denominator. When we were here and we were trying to show 2/3, I'm like, how can I cut this thing into thirds? And then I need to show 2 of those. But the first thing I focused in on was the denominator. I want to see where the thirds are. And then when we did this second one, it was 5/6. How can I find out where the sixths are? Those are in the columns. Okay, now I know where the 6 are. I'm going to go identify 5 of those. We started with the denominator and then worked on the numerator. Same thing here. Show 1/3. Well, I need to find where the thirds are and then show 1 of them. This is a little different because we aren't given what the 1 is at the beginning. Now we're going to turn our focus at the beginning to our numerator. This is 4/3. I want to identify where the 1/3 would be, and those here happen to be in the columns. Each one of those columns is 1/3. I have 1/3, 2/3, 3/3, 4/3. And then it's 3/3 that will be 1. So I need to circle 3 of those to be 1. Let me know if you have questions. These models can be a little different, something new, something you haven't really thought of this way before. I think they're kind of cool, they're kind of fun, but if there's anything tripping you up, don't hesitate to let me know. Awesome, okay. Let's look at some problem solving. 8 inches is what part of a foot? And when it says what part, really what it's saying there is what fraction of a foot. So 8 inches is what part of a foot. It's saying what fraction of a foot. And there's a couple of different ways you can do this, but if you wanted to look at the length model here, and we go from 0 to 12, and we say, all right, well, what matters to me is this 8 right here. Okay, What fraction of a foot is that? Well, if I have that 8, if I cut that in half, that's 4. And if I kind of look at this whole thing as saying, well, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would be 8/12 of the whole foot. And then you could just reduce that fraction and you'd have your answer. So 8/12, let's see, those are both even numbers. So I could divide top and bottom by 2 and say that it's 4/6. They're still even numbers. I could divide again and say 2/3. And so 8 inches is what part of a foot? It's 2/3. Maybe you feel like I didn't get a whole lot of value out of the length model in that one. That's okay. One thing you can see here, once we get that answer of 2/3, if you look at this as 1/3, 2/3, 3/3, and it's easy to see we're at 2/3. If you look at it, instead of looking at those individual 1/12, by chopping our foot into 3 pieces, 8 inches is at 2 of those 3 pieces, or 2/3 of a foot. So that's a way to sort of illustrate the idea that 8 inches is 2/3 of a foot. We're going to turn our attention now to the area model. We have this picture here, and my question to you is, what fraction of that diagram is shaded? What fraction of that diagram is shaded? Be careful here. I don't think this is an easy question. What fraction of that diagram is shaded? Oh, no, I wasn't going to do a poll for this. Just throw an answer out there, Courtney. Good question. Sorry about that. It does feel like the kind of thing that I would do a poll for. 1/8? Anybody else have something different? We have 1/8 as a proposal for this one. If we're all good with 1/8, 1/5. All right, so let's see here. When I try to figure out what fraction is shaded, one of the things that matters is how many pieces there are. We've got an agreement on 1/8. Let me do this real quick. If we go over here and I change my circle and I draw it like that, and I shade this one right here, what fraction of that circle is shaded? We'll just keep it simple. Over there with the blue one, what fraction of that one's shaded? 1/4. I agree. I agree with all of you. 1/4 of that one is shaded. We've shaded in 1/4. And there's 2 ways to think of that. One way is, well, there were 4 pieces and I colored in one of them. What really matters, though, is that all of those pieces were the same size. In order for me to say 1/4 of this is shaded and there's 4 pieces and one shaded, they all have to be the same size. When they're not the same size, we have to sort of change the way we look at this. Instead of, like, I could look at this picture and say there's 1, 2, 3, 4, 5 pieces. One of those 5 pieces is shaded, so it's 1/5. Seems like a reasonable answer. The trouble is that not all the pieces are the same size, so we're not going to go with 1/5. Instead, we're going to think of it in the other direction and say, over here in our blue one, how many of these would it take to fill up the whole circle? And it would take 1, 2, 3, 4 of those to fill up the whole circle, so it's 1/4. And we're going to use that same logic over here in the green shading and say, how many of these would it take to fill up the whole circle? Well, it would take one, let's see, that would take one here, and then another one here, and then a couple more over here, and then a couple more over here, and then a couple more over here. It would take 8 of those to fill up the whole circle. So what's shaded there is 1/8 of the entire circle. If the pieces are all the same size, then we can just look at what fraction of the pieces are shaded. If they're not the same size, then think of it from a little bit different perspective and say, how many of these pieces would it take to make the whole circle? Hopefully that helps fix that up, and we can see that that's 1/8 of the whole circle is shaded. Here's one that I don't think is easy. In the diagram, if the diagram below is 1 3/4, show 1. So if that's 1 3/4, what would 1 look like? Now, we did problems like this before where, if we had a rectangle and the rectangle was 1 and we wanted to show 4/5, we colored in 4/5 of it. That was fine. This is a little different from that. This time we've been given something that's not 1. We've been given something that's 1 3/4. And we're trying to show where 1 would be. So take a minute, try to think this one through. I don't think it's an easy question at all. And then we'll talk about it together in a minute or two. Some of you who are very, very good visually might see this without too much trouble. Others, I'll have an approach for you that works better for me because I don't always see things right away. And I didn't want to do a poll for this one, but I'll just throw it out there. How many boxes will there be when we go to show 1? How many boxes will there be when it's 1? Right, a couple of 4s over there. Very good. Courtney and Leslie, that's excellent. Lisa, very good. And like I said, some of you may just sort of see this. If you don't, that's okay. Here's what we're going to do if you don't see this right away. We're going to say, okay, what you've given me in this diagram is 1 3/4. And that's written as a mixed number, and we haven't really talked much about those yet. We're going to get into mixed numbers a little later on in more detail, but you might remember that 1 3/4 is the way to rewrite that as an improper fraction is we do 4 times 1 plus 3. And so 1 3/4 is the same thing as 7/4. And so this picture I have here is 7/4. Well, if this picture I have is 7/4, and what I have then is 1, 2, 3, 4, 5, 6, 7 objects. So I have 7 objects that represent 7/4. It'd be great if I knew what a fourth was. And well, let's see. If I have each of these as 1/4, that'll be 1, 2, 3, 4, 5, 6, 7/4. So this picture is 7/4. If I want to show 1, what I need to show is 4/4. And so that's going to be over here with 1, 2, 3, 4/4. What some of you may have been able to do here is to look at this and say, if that's 1 3/4, perfect. That's great. If you can visually sort of see, hey, if I make 4 boxes 1, then the other boxes is 3/4, that's fantastic. That's great. But if not, then you can sort of take this number, convert it to a mixed number, and then sort of go from there to figure out how many boxes you'll need to make 1. Let me know if you have questions. Got a couple more problems we're going to solve. Today's going faster than I thought. Like I told y'all at the beginning of the semester, some days I will go faster than I think. Some days it go slower than I think. Today's one of those going faster than I expected. Another problem solving with area. 4 ounces of medicine is in a bottle, and a dose is 1 1/3 ounces. How many doses are in the bottle? And some of you might think right away to go to dividing fractions, and that's okay, but let's look at this from the prospect of somebody who doesn't know the algorithm for dividing fractions. Instead, they're just going to use a model to solve this. I have 4 ounces of medicine, so I'm going to make my 4 ounces. There's 1, 2, 3, 4. Those are my 4 ounces of medicine that are in the bottle. I've made a little area model showing those 4 ounces. And a dose is going to be 1 1/3 ounces. Because 1/3 is an important part of this dosage, I'm going to cut all of my circles into thirds. It doesn't have to be a work of art. We're just cutting them into thirds. All right, so I have my 4 ounces. I've cut them all into thirds. And now what I'm going to do is I'm going to start parsing those out into doses. So the first dose is going to be 1 1/3 ounces. So that'll be 1 1/3 ounces. I want to make sure you see that before I go forward. But what I've done here is I've counted, here's a whole ounce, and there's another third of an ounce. So 1 1/3 ounces is that first dose. Then I'm going to go do the second dose, and that's going to be 1 1/3 ounces. Well, there's 1 1/3 ounces. Because remember, I chopped these into 1/3. So when I'm going to show 1 1/3 ounces, this one's a third, this one's a third, this one's a third, and this one's a third. So I need 1 1/3 more to make a dose. Let me know if you have questions as we go through this. I think you know what's going to happen next. I need to make another dose, and that's going to be 1 1/3 ounces. How many doses are there in a bottle? There are 3 doses in the bottle because I just took those 4 ounces, divided them up into 1 1/3 ounce doses, and found out that there were 3 of them. I don't need to know anything. The thing that's exciting about this that I think is cool is maybe you already know how to divide fractions, but if you don't, you can be a pretty young kid and do problems like this, having no knowledge of how to, manipulate the numbers to divide fractions at all. You just use an area model and you can solve the problem. I think it's super cool. All right, I have one more I want to look at with you. It's another area model question. There was a bowl of jelly beans on the table. Larry ate half of them. Then Mo ate 1/4 of the remaining jelly beans. And then Curly came along last and ate 2/3 of those. There were 4 jelly beans left over. How many jelly beans were there at the start? There's a lot of different ways to do this. The way that we are going to talk about it is very similar to the way that Jose bought the chocolate and we wanted to know how much an entire pound would cost. That's kind of what this is. We're going to use an area model. We're going to chop it up into pieces. Once we know what one of the pieces has in it, we can figure out what all the pieces together will be made up of. Let's go ahead and take a look at this one together. I think this is sort of the pinnacle of problem solving using the area model. It's excellent. It's a really cool thing. So there's a bowl of jelly beans on the table. We used a circle last time. I'm going to use a rectangle this time. There's a bowl of jelly beans on the table and Larry ate half. So I can cut this rectangle in half and say, here's what Larry ate. Those are gone. Those have been eaten. Then Mo ate 1/4 of the remaining jelly beans. So what I'm going to need to do is, just looking at the remaining jelly beans, just down here, I know that Mo ate 1/4 of those. So I need to cut that into 4 parts. And I was told what Mo ate 1/4 of those. So here's what Mo ate right there. Let me know if you see something that doesn't make sense or you're not sure where it came from. Okay, and then Curly came along and ate 2/3 of what was left. So we have to look at what was left, and Curly ate 2/3 of what was left. How many boxes is that out of what's left? How many of those boxes did Curly eat? Excellent, Xochitl. Excellent, Leslie. Curly ate 2 of those, and now we're told that there were 4 jelly beans left. So we get down here to the end, and I have 4 jelly beans left over. What that means is each one of these boxes down here represents 4 jelly beans. And when I go to look at the top, and this is an important part of this, I need to section it off into pieces that are that same size, because a piece of that size represents 4 jelly beans. And so now I can see how many jelly beans were there at the start. 4, 8, 12, 16, 20, 24, 28, 32. There were 32 jelly beans at the start. Larry ate 16, Mo ate 4, and Curly ate 8. And we can see that when we look at our diagram. That is a really valuable tool that we have when using the area model to solve problems. You'll see some like that in your homework for sure. Okay, so this is our